So we're pleased to welcome Dr. Julien Cohen-Adad to present on spinal cord image acquisition. Dr. Cohen-Adad is a professor at Polytechnique, Montreal, associate director of the neuroimaging functional unit at the University of Montreal, and co-director of the neuroimaging research laboratory at Polytechnique, or NeuroPoly. He holds the Canada Research Chair in Quantitative Magnetic Resonance Imaging. Perhaps more notably, Dr. Cohen-Adad's team has developed the Spinal Cord Toolbox, which has become the standard software in the academic and medical imaging sphere for spinal cord image processing and analysis. And I would not have likely finished my PhD without the spatial normalization tools available in SCT. So thank you for being here.
Thank you so much. Stay here, Ken, because I have a little present. So this is actually an MRI phantom for preclinical scanner that is filled with maple syrup. So it's like it has similar permittivity and conductivity as human flesh. So there you go. Enjoy your experiments.
Thank you. Thank you. Did you pay the tariffs on?
It was bought in Canada, and I didn't tell anyone. All right, so yeah, it's a pleasure to be here. Thank you very much for the invitation. The talk is going to really focus on the acquisition and yeah, mostly the acquisition, in fact, because the analysis will be talked about later by Sandrine Bédard. And one of the aspects that we always show is the fact that the spinal cord is a tiny structure, and I like to show the brain and spinal cord side by side to really make people realize that when we want to go into the internal structure of the spinal cord, we need to, we really need sub-millimeter resolution. And as you know, when we are asked for better resolution, it comes at a cost of SNR, signal to noise ratio. And there are ways to gain SNR because, as Gary mentioned, the NMR by essence is an extremely low SNR tool. And in order to maximize the sensitivity, then we could better engineer the receive coils that we put around the region of interest. And there have been quite a lot of different designs for receive coils in the spine area. So I encourage you to look at the different papers. And then, in addition to the RF coils that deserve better engineering, we could also, if you have a couple of $1 million in your pocket, get to higher field strengths. That will also boost the SNR and the contrast to noise ratio for fMRI experiments. And there have been a couple of applications now on 70 spinal cord MRIs from the Marseille group, led by Virginie Callot, showing some nice quantitative MRI, based parcellation of the cord. I've done some work while I was at MGH with Anne-Louise Aucklander, where we imaged patients with spinal cord injury. And we really showed the benefits of 70 by showing those very tiny, hyper-intense lesions above that very big lesion that could be seen at 3T, but that myelopathy could not be seen at 3T easily. So that was one of the advantages of going to a higher field. And similarly, 70 applications in the patients with amyotrophic lateral sclerosis. And obviously, one of the workhorse of 70 is functional MRI because of the increased sensitivity to the Bolt signal. And Rob Barry, among others, have shown also some applications at 70. And I'd like to spend maybe a few slides showing, all those technologies together, meaning advanced coil designs and 70 imaging. And so we started working on it a couple of years ago. It was a collaboration with the Robarts Institute in London, Ontario. And so Kyle Gilbert helped us with the proposed design of dipole for the transmit part of the coil, because what you need to know is that when you go to 70, you don't have the luxury of having an already existing transmit coil. You need to bring your own transmit coil. Not without going into too much details, transmitting at 70 is also tricky because the homogeneity with which you excite all the spins of the region becomes much less large. So it has to do with the wavelength across magnetic fields, and the wavelength at 70 would be around 30 centimeters, which is kind of the size of the region that you want to image, whereas at 3T would be more 1 meter. So you don't care too much about transmit homogeneity, whereas at 70 you do care a lot. For the receive part, it was built by Nibardo Lopez Rios, one of the research associates in the lab, and he went with a soccer ball type of design. It was introduced by Graham Wiggins 20 years ago, so also even more than that, I think. And so these are the some of the examples of individual channels of this soccer ball design for the posterior and for the anterior part of the cord. And then when you combine all those images together, you get some nice coverage that goes down to about T3, T4 level. And I was talking about homogeneity of the transmit. So that's something that is critical. And thanks to the parallel transmit system of the Terra system, we're able to drive those dipoles with individual magnitude and phase in order to homogenize the tip angle within the region of interest. And so we basically ran Spinal Cord Toolbox, segmented the spinal cord, and then with shimming toolbox that Alexandre Dastouth will tell you about, we're able to compute the shim coefficients necessary to get a homogeneous transmit inside the whole cervical spinal cord. And what you're seeing here are B1 plus maps and pictures of the coil. So that's how the coil looks like. It can basically open and close. And then since we are pretty happy with this design and Rob Barry was becoming a bit jealous, we built one for him that is now sitting, taking dust somewhere at MGH. So if you want to do a trip in Boston, you're welcome to use the coil. And then we wanted to, we got, a lot of discussions with the spinal cord community, but I'm getting a new 70 scanner. I'm not really sure what coil I should get. Do you have some ideas? There's MR Tools, there's Nova Medical, and so there's Rapid, and so we decided to do a traveling spine study. I was quite a bit of work to get 3 participants flying all around the world, mostly North America and Europe, and being scanned across 8 different scanners equipped with 4 different coils. So we tested, so our coil is here. We tested the Rapid Biomedical, which is an 8-channel transmit receive. Also a coil from MRI Tools that is equipping the MPI in Leipzig, and also group of Johanna van Escho in Trondheim, and then another custom coil in New York, and that's Alan Zeifert's site. And so we basically created protocols, making sure that the versions of the scanner were compatible with the protocol. So that was really like a bit of a pain to set that up, but eventually we did, and so we got this paper describing transmit field, but also receive sensitivity across 4 different coil designs. And I want to also give you a sneak peek of what we are currently working on, including also the brain in the story, and so we're working on the dipole-based 60 receive channel for that covers the head and the neck as well. Hopefully we'll be able to get down to T3, T4. okay, so you have a scanner, you have a coil, then what? There is quite a lot of quantitative MRI techniques. If you go to ISMRM, every year there are new acronyms that come up. Like STEADY, CHARMED, NODI, and many things related to imaging myelin, imaging axons, axon orientations, and so on. So picking the right method, can be a bit of a challenge. And then when you finally decide that you want to do NODI, then you're sitting at the console and you're like, okay, so what TR should I use? What TE? What flip angle? What bandwidth? And what coil? And so on. So for new researchers getting started with spinal cord imaging, this can be pretty overwhelming. And a lot of pilot scans, a lot of time and money that is wasted, and that many other groups in parallel are also doing, right? So why not, sharing this experience and then come up with some sort of generic guidelines. So that's what led to the so-called Spine Generic Protocol. So it's an initiative that started in 2018 while I was doing my sabbatical in Tokyo. I had access within I would say a 20-meter diameter. I had access to 3 different 3T scanners from the 3 brands, GE, Philips, and Siemens. And the Canon scanner was not too far. So it really pushed me to start setting up some generic protocol that could be used across scanners. And one particular aspect that I want to stress is that this protocol is not bound to particular disease, right? So people working on MS, they contact me and say, oh, can I use the Spine Generic Protocol in patients with MS? And I say, yes, but you also need to adapt it to the particular disease, maybe add a flare, or like add some relevant scans that are typically used in clinic. But this Spine Generic Protocol is so obviously customizable. You can, if you have like a new SIMA X, for example, then you want to reduce the TE, obviously, because you can. So don't just download it and apply it, but you might want to adapt it. And we try to provide updated versions on GitHub for the newer models and newer scanners. And the purpose of this protocol is to be able to generate nice looking T1 weighted anatomical, which are used for segmentations, T2 weighted with a better resolution, which are also used for segmentation of the cord. And this segmentation of the cord can give you cross-sectional area, which is a relevant biomarker for spinal cord atrophy, for example. It could be used to compute compression metrics as well. It also includes a multi-echo gradient echo sequence, so T2 star weighted with high in-plane resolution. And that's used for segmenting the gray matter. And if you have the cord and the gray matter, then you can get also the white matter. And also some so-called microstructure imaging techniques, diffusion-weighted scans at 0.9 millimeter in plane, and MT protocol. So you could do magnetization transfer ratio, or you can do MT-SAT with it. Very importantly, this protocol comes with a standard operating procedure, similar to what Ken was alluding to during his talk about how to position patients, how to minimize lordosis, simple things like the type of cushion you're using. If the cushion is 1 centimeter too large, then there will be more lordosis or less, and then it's going to affect the quality of your image. Comes with a bunch of screenshots to show how to position the FOVs. A bit more complicated for diffusion, because depending on the license or the scanner you have access to, you might be able to use 2DRF or Zoom based approaches, or if you cannot, then you need to use SAT bands. And the goal really is to reduce the matrix size and minimize susceptibility-related distortions. Okay, so that being said, the first images we got with that protocol across vendors were pretty satisfactory. In terms of harmonization, we were trying to get similar images across vendors. So that's the T2-weighted image, sagittal, and then axial images for T1-weighted from the MP range, T2-weighted, T2 star-weighted. That's from the MT protocol, MT1. That's the T1-weighted from the MT protocol to be able to compute the MT stats and the diffusion-weighted imaging. Okay. Okay, so it's a bit boring to always look at nice data because that's always the thing that people show in publications and in conferences. And what I'm really interested in always is, I want to see artifacts. That's really what excites me because there is room for improvement. If the data is perfect, then my job is done. So we're going to play a game here. You're all going to participate. Some of you might know about this artifact game that is happening every year at ISMRM, and we're going to play that game now. So don't be shy. So this is a T1-weighted image, okay? And the first question I'm going to ask, and I know people are shy and stuff, so we're just going to do it with a raise of hands. Okay. So the first question is, who thinks the artifact is on the left? Okay, who thinks the artifact is on the right? Okay, so the artifact is indeed on the left. And now can someone tell me the source of the artifact? So this kind of a blurry aspect of the chord, like the chord boundary that is, much cleaner and sharper in this image. Yes. Motion, yeah. And motion of the patient, you think, or
breathing, respiratory motion.
Respiratory motion. In this case, possible there is a bit of motion from the subject. I would tend to favor, in this case, a more pulsatile motion because we see patients with where there is narrow spinal canal, and the cord is actually pulsating quite a lot, and it appears pretty well in the MPRH image. So it's possible that there was also respiration and subject motion, but I think there is also quite a lot of spinal cord pulsative motion. All right, another one. So who thinks the artifact is on the left? Who thinks the artifact is on the right? Okay. All right, it's okay. So yeah, I think the majority won. And the artifact is shown here with the red arrow. So you see this kind of hypo-intense signal directly inside the cerebrospinal fluid, where you would not expect that. Ideally, you would have like a clean, white, hyper-intense CSF. So what is happening here? Yes, Marvin.
Is it the overflow artifacts?
Overflow? What do you mean by overflow?
Some sort of CSF artifact?
Yeah, it is indeed. I mean, yes, it is actually a CSF artifact. So it would be the spins would be saturated, and also because of the flow, they would not recover enough to give a signal. And it's actually very interesting. If you're sitting at the console and you're seeing this artifact, just increase the TR and you'll see the artifact disappear progressively. So one way to get rid, and in fact, the reason we got these images from one site, and they actually they used the wrong flip angle, right? So you could either increase the TR or you could also reduce the flip angle. In this case, they used the flip angle of 180 as opposed to 120, which was the prescribed flip angle. And so we got a systematic artifact in all the subjects coming from this site. Don't hesitate to interrupt me. Yes.
How do you know if that was artifacts or not? Let's say you
and not genuine anatomy. Right. So there is indeed nerve rootlets and so on that are seen as hypointense signal. This is just like a very large area. So I would not. By my experience is that when I see that, it's usually like an artifact. And again, as I said before, when I'm sitting at the console and I just increase the TR, this just becomes pure CSF. Right.
Julien, how does it? Because you also have like a hyperintensity in the cord, in the anterior portion, right? Up above that part, that white band.
This one?
That related to CSF flow too? Somehow?
But might be, some people have a slightly bigger canal. Could be that. All right. So game is on. Game is on. So who thinks the artifact is on the top? At the bottom? Right. Good. So what could be? So that's pretty ugly, right? So we're looking at axial views of GRE scans. So what's the problem here? This one is unfortunately quite prevalent in this type of sequence. Yes.
Mm-hmm.
Yeah. That would be like a subject motion, fortunately. Yeah. Yeah, there's not a lot we can do about it. So we're moving to diffusion-weighted imaging, showing you a couple of views: a coronal, sagittal, and axial view. One acquisition, one subject on the left, one on the right. Who thinks that the artifact is on the left? On the right? Yes. And what could be the problem here? So, we see that the image is a bit darker. Seems like, in some parts of the image, the signal is kind of attenuated. What's happening? Yes.
Shimming?
Yes, shimming. And more specifically, how could shimming, like poor shimming, cause this? Well, the thing with shimming is that it's that's we always think, well, with poor shimming we get some distortions, but here we don't have distortion. We have like a decrease of signal. So it's shimming associated with another pulse that is applied on the sequence, and this pulse is a fat-sat pulse. And the problem with poor shimming is that because we have a strong offset in the field, the fat-sat is actually saturating the water. And so what we end up doing is we saturate the water, we get less signal, and as a result of it, our fat-sat is also much less efficient. And so you end up with these kind of images. Here I'm showing the B0 image, and here I'm showing the DWI mean image, right? And you see those like ugly, non-saturated fats that is just like warping around everywhere. So shimming can have very like disastrous effects and manifest in many ways. Okay. I really like this one. So who thinks that's going to be easy? Who thinks the artifact is on the left? Okay, on the right, yes. Okay, yeah, very good. Right. So what's happening here? So it's a sagittal view of a diffusion-weighted scan, the mean diffusion-weighted scan. And what I should tell you also, because that's what I'm going to tell you, is going to help you find out what the problem is. This is a mean DWI, which means that all the diffusion-weighted images have been acquired systematically with this kind of weird pattern. So it's hard. So are there any Philips users here in the room? No, so that's why. Yeah.
Does that have something to do with the case-based pattern? So
Not really.
Okay.
Not really. So Philips zoom sequence. So the zoom sequence. So on Siemens and GE, if you want to do reduced field of view, you would use 2DRF. On Philips, it's different for the diffusion weighted sequence. You would basically use like refocusing gradients that are orthogonal to each other. So some of the spins would be refocused and some would not. It's a similar principle when you want to do MR spectroscopy in order to just excite one particular voxel. So that's the technique they use on Philips. And the Philips diffusion sequence has concatenation. And what they do is, in fact, they would acquire odd lines or like odd slices for the first couple of minutes of the acquisition, and then the even slices for the second part of the acquisition. And what happens if patients move? You have something like that. And I can tell you it's very tricky to correct for motion when you have an image like that. So it's a combination of subject motion and a zoom concatenated feature on the Philips scanner. Another one, diffusion weighted scan. Now I am not showing the mean diffusion weighted, but I'm showing individual diffusion weighted volume. And what you're seeing here are like small patterns, small like hypo-intense patterns. So would you have some ideas of what could be happening here? Yes?
Susceptibility.
It's not susceptibility. So if you're sitting at the console and you're running a diffusion weighted scan, you would see that sometimes. You would see, if you look at the axial views of the spinal cord, you would see that sometimes spinal cord disappears and it's not related to the diffusion encoding. It's related to something else, or like it is partly related to diffusion encoding, but also to something else. So diffusion encoding is very sensitive to motion, right? Because that's what you're effectively measuring. But it's what you want to do is weight microscopic motion, microscopic diffusion of water molecules. But what happens if you have a bulk motion of tissue? You lose all the signal. That's what's happening here. Because of pulsatile motion of the cord, during the systole and then the diastole, the cord does not move with the same speed. And if you happen to acquire a slide during a very strong motion of the cord, then you would just lose the signal in the cord. And that's what people like to do, cardiac gated acquisition. And this acquisition was non-gated. If you do gating, you would see less of this, right? But then if you do gating, you also have other issues, variable TR, longer acquisitions, and so on. Yes?
Julien, is the gating protocol always, is it standard setup for spinal cord motion?
It's the spine generic one is gated, I believe.
Yeah,
but
is the gating optimized for spinal cord? I don't know how it works necessarily.
Well, it's basically cardiac dependent. Yeah, but there are also a couple of papers where we ask the question. Actually, we have a paper that says to gate or not to gate, and that is a question because you could acquire way more volumes with some artifacts here and there, but there are also some robust fitting for the different tensor, for example. So it's not necessarily a bad idea to not gate. So it's an open debate. But it's good to be aware of that at least. Okay, another one. So we think the artifact is on the left. Okay, on the right. I was being very mean here because if you look the issue that you're observing here is kind of happening there as well. So what could be the problem here? Yes.
Was there anything to do with coils?
Yes, that's it. It was a wrong coil selection. So people, I think, just instead of downloading the generic protocol and then running it, or maybe it was a GE. Maybe it was on a GE system where you have to actually select the coils, but yeah, the coil selection was incorrect, and so they basically forgot to activate this element and that element. If you have no coil, you have no signal. Another one, it's not really an artifact, right? But when you manage multi-center data and then you receive data that says that this one is an empty off and this one is an empty on, and you're analyzing your images without looking at the data, and then because you have hundreds of patients, and then you look at some results and you're like, this MTR for this patient is not correct. What's happening? Then the first reflex you need to do is to look at your data. So when you look at your data, that's what I did here, and then I realized that the naming of the sequence was actually swapped. They called empty off empty on and empty on empty off, right? And then they send it to me and say, analyze my empty data. And yeah, obviously that's a problem. And a bit more sneaky as well is when shim parameters change within a quantitative MRI protocol. When you acquire, multi-echo T2 or like empty sats, where you have to acquire multiple volumes, you need to acquire them with the same parameters, or like you should be changing only one parameter, one TR or one flip angle. In this case, I don't know what they did, but the shim parameters changed, and as a result, the signal intensity changed, the FFT scaling changed. So basically, you cannot compute a proper quantitative metrics with that. So it's little things to be extremely aware of. Okay. So that being said, we tried to get multiple centers acquire data. How much time do I have? Is it until 11 or?
You have until 11:05, so 15 minutes. You have a lot of time.
Okay, good. Okay, so we asked multiple groups to use this spine generic protocol, and then come up with data sets that was organized using BIDS standard, naming standard. So as you can imagine, there was a lot of logistics involved in terms of naming the data set, converting it, shipping it, and also versioning it using Git and Git Annex on different servers so that everybody could download this data. So this data is open access. There is multi-site single subjects, that's me, and then multiple like other subjects, 267 total. What's nice is that the project is ongoing. So if you wish to participate in this database, it's still open. You can contact me and say, hey, I want to scan with this new scanner. Can I contribute to this database? And then a big yes, you're welcome to. I told you about the sneaky parameters that could change. If people are not careful, they might use a different TR, they might use a different flip angle or shimming. And we implemented a strategy to have a continuous integration verification of the parameters that people use to acquire those data. So BIDS has a package called PyBIDS that can validate multiple things. It can validate if the data is according to BIDS. It can also validate that the parameters are correct, are within an asked range according to the Spine generic protocol. It can also check that the TSV, the CSV files are correct, and it really saves a lot of human work and makes it also more reproducible. Because instead of having, grad students say, hey, can you check this data we received from the collaborators just to make sure they are okay? We have now a robot to do that, right? Obviously, humans are still needed to just look at the data. It's always important, but at least, part of the mistakes could be caught with GitHub Action. And so the way it works with GitHub Action is that every time there is an update on the Git repository of the dataset, so let's say we have new subjects, we push them, and then GitHub Action runs automatically and runs all those tests. And there's also a front page for this project. It's hosted on SpineGeneric rtfd.io. And it has a lot of, explanation, documentation, if you want to rerun the analysis, right? So the analysis pipeline, I'm going to show you briefly how it consists of, but there is the T1 weighted that was segmented, and then the vertebrae were labeled, and then all these subjects were registered to the PAM50 template. The same was done, and so that's enabled to compute the chord cross-sectional area. Same was done for the T2 weighted scan, segmentation, registration to PAM50. The multi-echo gradient echo was segmented for the chord, but also for the gray matter in order to compute the gray matter cross-sectional area. The MT-SAT protocol was co-registered, segmented, and the gray matter was segmented to, or actually no, the gray matter was not segmented, but we registered the chord to the PAM50 so that we can then warp the white matter atlas onto that space, right? And then extract MTR, MTSAT, and T1 within the white matter. And similarly, the diffusion weighted scan were motion corrected, segmented, and then the white matter atlas was warped into the space so that we can compute fractional anisotropy and all those different flavors of diffusion weighted scans. And you will know more about this data analysis this afternoon. But without further ado, I'm going to show you some of the results of the SpineGeneric protocol. The first thing we want to look at is the data. So if we create a mosaic of all the scans that were acquired across the 267 participants, this is what we get. And then we can observe, the fairly good consistency of FOV placement, contrast. You see that in some cases, some sites some mistakes here and there, but I would say overall it looks pretty good. And then from these scans, we segmented the chords, and then we computed cross-sectional area across C2, C3 level. So now you're all experts in spine anatomy. And so what you're seeing here is the result. So it's a bit heavy to digest. So I'm going to describe, first of all, what you're seeing on the abscissa here are the different sites, okay? So we have the site La Sapienza in Italy. They have a Philips scanner, because Philips is blue, GE is black, and Siemens is green. And each red dot corresponds to a participant, okay? And so what is displayed here is the mean of each participant. And what is the dashed line here is the mean across participants and sites for a given vendor. Okay, so we can then compute the coefficient of variation intra-site. For each site, we have a coefficient of variation, and then we average it together. And we also have a coefficient of variation inter-site. Okay, so what is the variability of the CSA across the different sites? And we have that per vendor, right? So I think we know the cross-sectional area varies across individuals, so it's not necessarily relevant to assess the quality of precision of a protocol. What I find quite relevant is the inter-site variability. Because assuming that the variability across subjects is, smoothed out, we could then get, a COV, which is quite remarkable, and it, indicates how sensitive you could be to detect a subtle atrophy of the spinal cord. Similarly, we computed the white matter magnetization transfer ratio between C2 and C5, and then we could also map those different metrics. And some of the sites here use there's a red cross in Stanford, I'm sorry. I think there is just because there was like some version of the scanner that used another TR, and that just like screwed everything up in terms of the MTR variability. Doesn't mean that the MTR is wrong. It just means that the MTR is different from the other sites, right? So it's difficult to compare. But yeah, again, inter-site COV below 3%, so we are quite happy about this. And similarly for FA, from diffusion-weighted scans, also COV inter-site below 4% for the 3 different vendors. So that's quite nice. And then if you want to know more, you can go to Google and then type spine generic protocol. Then it will bring you to the page. And then on that page, you can, well, first of all, you can look at the data. And then you can see the different scans. You can play with the different views to have a sense of how the data should look like if you decide to acquire them at your site. And what you can also look at is the analysis pipeline and results. And so some of the results that I showed you are there, and you can also play with them because these are interactive graphs. So you can have the individual values for each site and each participant. And then have that for all the metrics. Okay, so that being said, the elephant in the room is what about fMRI? And historically, we decided as a community to not include fMRI in the spine generic protocol because there was still no clear consensus about how fMRI data should be acquired. That's why it's not part of the spine generic protocol. That being said, things could evolve, and maybe at some point, I think we should probably include that in the spine generic protocol. And there is a lot of excitement, partly from me, about dynamic shimming. So shimming is really the low-hanging fruit and the key game changer for Granular API. So I'm showing here an image from Jürgen Finsterbusch's paper in 2012, where he introduces the Z-shimming technology, showing how bad this looks like in the thoracic spine. As you can see here, those intravoxal dephasing are due to bad shimming. And really the key aspect is to shim individual slice. And there are technologies now that are available across different scanners, different vendors. Alexandre is going to talk about it, and I just want to show a sneak peek of an experiment that Alex did on the 70 scanner on the Terra system in Montreal, where I think it was like the first image of dynamic shimming, and it worked like a charm, which is rare when we do experiments. Usually it fails for the first 3 years, and then eventually it starts to work. This time it just worked like a charm the first time. And so this is really like the standard boring shimming, where we see those ugly ghosting. We just don't see the spinal cord at all. And with dynamic shimming, we start seeing some more consistency. And what's nice is that it's also consistent across individuals. And again, Alex is going to tell you all about this this Friday. So to conclude, advanced RF coil and ultra-high field system can really push the limits of spinal cord applications. So a lot of exciting time ahead. Spinal generic protocol, really the purpose is to promote replicability, dissemination of knowledge, facilitates the addition of spinal cord quantitative MRI protocols at non-expert centers, minimizes the variability in multi-site and multi-vendor studies. So really the question of harmonization. It's already implemented in at least 50 clinical sites and also in different initiatives. Inspired initiatives that is led by Claudia Weller-Kingshot, London, Zurich, Toronto, and the CanProco, which is a pan-Canadian 7 sites across Canada studying MS. With that protocol, we also have an open access database. And we also recently, actually, thanks to Marve, put together a multi-site gradient echo EPI dataset that is also hosted on Open Neuro. So there is more and more, open data initiatives. And finally, analysis tools, making them standardized really helps with reproducibility, but I really insist also on the transparency. It's very important for other people to know what analysis you did. If not, I think it's just completely irrelevant. Publications are irrelevant because we don't know what people did. It's very easy to make a bug on the code and people would not know about it. So transparency and replicability is absolutely crucial. And having those automated pipelines obviously also makes it much easier to run pipelines across hundreds and thousands of subjects. And then finally, all those technologies, they are nice and blah blah blah, but they are difficult to grasp. It requires quite a lot of expertise to implement them into your routine, and that's why communication is important. Publication is not enough. If you read an article, you're not going to implement all those technologies in 2 days. It's not going to happen. Which is why communication, meeting with different expertise is key. And that's why we put together those workshops. First one was actually in Milan. It was organized by Paul Summers in 2014. And since then, we continued organizing the spinal cord MRI workshop until Rob Barry took over, indeed, the Martineau Center. But it really started quite a while, and the community is growing. So it's beautiful to see that, and I'm glad that Ken, you took over this initiative. There was one that was happening actually a month ago in Marseille, organized by Virginie Callot. So you see there is a lot of initiatives and some people are not aware of them. So to make people aware of them, we should also improve our digital and online communication. And so one way to do that is this website called spinalcordmri.org. And on this website, you have a list of all the workshops that have been happening and also that will happen in the future. There's a mailing list that you can subscribe to where all these communications will be sent to. And on that website, there is also a link to a forum. It's a discourse forum where we send communication about upcoming workshops, but it's also a platform for our community to discuss with each other, ask questions. What coil should I use if I want to do this experiment? Do you recommend that I use a TE of 19 milliseconds or 25 milliseconds for my fMRI experiment? Questions on MR processing, image processing, and SCT. And then I added those a couple of weeks ago because I presented that. I did a talk in Marseille, and then Virginie was like, "Oh, why don't we have a forum?" And I was like, "But there is a forum." So the problem is that there is a forum that's been lying there for like years, and people are not aware of that. So I'm telling all of you now that there is a forum, and then my plan was to send to the mailing list, which has about 400 people on it, the link to the forum to say there is a forum. But before doing that, I just want to make sure that this forum is fine. So I'm putting that slide here, and I'd like to take 30 seconds, 1 minute to ask you if you think these are relevant topics. Because, you know, the issue with forums is that if they are not actively used, then they are irrelevant, right? So a forum is as good as, its activity. So what do you think? Are the categories okay? Should we add categories? Should we remove? Should we merge categories?
I'm liking the categories. Just to open it up this discussion a little bit. I guess it's challenging, like when you have like GitHub issues, right? And you post comments there. Is there a way to like for Spinal Cord Toolbox, right? If there's issues about Spinal Cord Toolbox, do you want them here or do you want them in issues?
Yeah, so I want them here.
Yeah.
This is the user-facing interface. GitHub is more for the core dev. Then what happens is that when we see a user posting an issue here, we would open ourselves an issue on GitHub. That is more technical. Yeah, but everybody's free to open an issue on GitHub as well. But this is much larger than SCT. It's really, contains the spinal cord imaging community. So think about it. If you have afterthoughts, you can also send me an email. You can post suggestions about the forum on the forum as well. I'm not sure what category that would fall into. That's the problem. But anyway, I'm probably going to advertise that, and then I encourage you to use that forum. And so with that, I'd like to acknowledge everyone in the lab. Not everyone is on the picture here. There was a bowling event. It's very funny, and we should do that again soon. And all the collaborators and funding sources, and thank you for your attention.
Any questions from the audience? Oh, yeah. Got it? Here, I can get the other one.
Thank you so much for the talk. I was just wondering, with the spine generic imaging protocol for DWI, are you able to do things like microstructural modeling, like NODI, with that protocol? And also, what about things like DKI?
Yeah, great question. So short answer is no. But that's why there was this little bullet points that I added when I introduced the spine generic protocol, is that it's customizable. So if you want to do like NODI, you would add a shell. Like currently it comes with one shell only, right? It's one shell at 800, I think.
Yeah.
Because we had to basically adapt all the different scanners that existed. So you can add one shell, you can add multiple shells, and then you can do DKI, you can do NODI, steady, and you name it.
Cool, thank you.
We have a question online from Katie Martucci. I am going to ask her to unmute.
Okay. Hello. Wonderful talk, Julien. Thank you so much for giving all that information. It's really helpful, especially the artifact part. I was wondering, well, no, actually, I just have a comment about the forum. I think even if people aren't actively using it, I think it's still a great resource to be able to have a place where users can search for past queries. So I'm assuming that you can search through things and it kind of can act as a resource for problems that other people had. Is that the case? I don't know if I saw a search bar on there, but I'm assuming there's a feature.
Yeah. Thank you so much for the question. So it was hard to understand fully, but it was about the search option on the forum, right?
Yes.
Yeah. Okay. It's a fantastic question. Fantastic, because I've been obsessing on that for quite some time. So you see my screen, right?
Yes.
Okay, good. So Discourse is a great forum technology. I don't know if some of you are aware of NeuroStars, but it's a very big forum for the neuroimaging community. And so it's the same technology, and it has categories that that's Spinal. That SCT. Okay, so there are categories, as you can see, but there are also tags. And if you want to create like a new post, you could choose the category. Okay, it could be under MRI acquisition, but you can also choose tags, right? And so tags, you can create them, or you can use the tags that are already existing. And so, for example, if you have a question about distortions, there's already one. If you want to use, I don't know, something about, motion, for example, then you can create a tag motion, and then, I did it. So there's a new tag motion now. And then you can ask your question and so on. And then the search function would be here, right? And the search function would use those tags. You can search with metadata, you can search with tags, you can search within particular categories and so on.
Okay, that's great. Yeah, I mean, even if people aren't actively using it, posting questions and things, just having it as a resource to search for things is really helpful. So
yeah,
that's great to know it's there. Thank you.
Welcome.
Right. Any additional questions from the audience? Anything online?
No, not. Feel free to post Q&A as well for our online attendees. You can also post it anonymously. You are anxious some MRI aspects, yeah.
Yeah, I have a question, Julien. So just maintaining the spine generic protocol, and when you're having multiple version changes and all of that, one, could you just mention how you do that?
Yeah.
And then also, if there is an immediate change, how do we request those?
Also a great question. So I'm going to show a very concrete example of what happened with someone you know very well that actually inquired about the SIMA-X.
And Julien, ideally, should I have posted on forum MRI acquisition? Or this is fine?
Yeah. I think it's fine. Imaging protocol here. Okay. Is that right? Where is it? Imaging protocol. Yeah, that's not very intuitive, and we should maybe. Okay. Anyway, so that's the GitHub where the protocol is, and it could be downloaded for the different vendors. But for Siemens, there is no SIMA-X yet, right? So, but there is an issue. It was opened by Merve. Thank you so much, Merve. Because this is what makes, as simple as that, for any open source project, they live if the community is actively maintaining it. So, it really defeats the purpose of having an open source project being maintained by only one person. It's not gonna work. So it's a community driven effort. It's very important to be aware of this. That being said, there is also I'm just going to showcase this and then answer your question more thoroughly. But yeah, so is there a protocol for SIMA-X? No, there is not. And then Merve, kindly offered to work with Christine, I believe, to basically try to make something up on the SIMA-X, and then eventually we would convert something that could be uploaded, and then it would appear for everybody to use. Now the bigger question of how, is it going to be there in 20 years? I don't know. It's comes back to the question of governance for open source projects and for all the projects in general. It's right now, I have, the rights to push on the repository. Other people have not, but we could discuss, and that could be a topic on the forum, to create a governance committee of multiple people, multiple institutions that have the rights to push the same way they do it for bids. That would make it more sustainable.
All right, and then we'll be using the new coil or new sequence today, and then we can see how it compares.
Okay.
Maybe confirm that it's as close as possible to the other protocols. Any additional questions from audience or online? No.
I'm wondering what's your thoughts on which kind of sequence to use for MRI for spinal cord disease imaging that can be used for deep learning or machine learning applications for spinal disease like stenosis or vertebral bone fractures or osteoporosis. Any of them? Do you have any?
For better diagnosis, and because you also mentioned about deep learning and machine learning. So
yeah, for diagnosis, like because there's so many sequences and technologies you can use, right? So is there anything that you think would work better?
I'm not so much an expert in tuning the sequences for neuroforaminal narrowing, for example, or spinal stenosis. There was a challenge recently, an RSNA challenge about different lumbar and sacral spine disease. So they used a protocol that was probably set up by like multiple radiologists. That was, I would say, probably the state of the art in radiology right now. Someone is going to present a bit of this this afternoon about those like spine disease and the challenge, but specifically about the sequence parameters and so on, I would not be able to advise you with high confidence.
Yeah, and during the panel discussion, we'll have Hugo Decker here, neuroradiologist, and he's involved in choosing what protocols make it into at least Stanford hospitals, and so he can probably answer some of your questions on there. Typically, here you're going to get a T2 and T1 sagittal series, axial series. They typically get the multi-echo gradient echo or germetic sequence as well, with or without that SAD and contrast. But that's what's done clinically. The big difference with the T1 and T2 weighted imaging in the generic protocol is that it's 3D and much higher resolution, allowing better quantification of the cord morphometry. But we see these 3D sequences used occasionally, but not always. And I had a conversation with Hugo about this, and I'm really looking forward to getting his thoughts on why they don't use the 3D imaging.
Yeah, I was at a hospital in Montreal, like a trauma hospital, 2 weeks ago, and asked the same question because they regularly use sagittal stick slices. They don't really use like isotropic resolution scans, and we like that because when we quantify like the 3D structure, then it reduces the bias for segmentations and so on. But since they don't do segmentations, they just want to like look at the anatomy on nice looking images. So that's why having those convergences is relevant, because is segmenting the structure really relevant? I don't know. We are just working on developing biomarkers, but some biomarkers might not be relevant. So yeah, it is a key question.
Got another question. So in the GE, your comparison between GE, Siemens, and Philips, let's just say cross-sectional area to focus on. If the G is systematically lower cross-sectional area than Siemens and Philips, I believe. And just curious, why?
Yeah, is it the case?
Yeah.
Is it the case?
Thought so, right? Yeah.
Yeah.
Not a lot, but it looks lower than Philips and Siemens.
I think that has to, so it could be due to a couple of things. It could be due to the parameters that are not exactly the same in terms of TRT, flip angle, and so on. And though if the contrast changes slightly, then the algorithm to estimate the chord boundary would also change. Filters that could be applied by vendors could also play a role. Yeah, that would be my guess. And another guess would be that all the GE sites happen to have people with a smaller cross-sectional area.
Yeah, I think with the GE scanner, there's a number of different filters you can apply, and I recall correctly, it's like they're labeled A, B, C, and D, which or whatever. It doesn't really tell us what A, B, and C do, which is
yeah. So for the sake of time, I did not show these sites, but we have the same quantification for the T2 weighted images, right? So that's on the paper. We see less of a variation here between the cross vendors. Resolution is better. It's 0.8. Maybe the contrast is closer between the three vendors. And what's interesting to look at then is the T1 versus T2 bias. And so there is a paper on that. But in general, the T2 weighted images show a larger chord than the T1 weighted. Obviously, these are the same chords, right? So it's just a question of the algorithm capturing, a different definition of the chord boundaries. Yeah.
And then for cross-sectional area, are you preferring T2 then over T1?
I think we do prefer T2. Yeah. It's cleaner, sharper.
I know you guys have published about this before. I just can't remember. But in line with all of this, in line with some of trying to understand how this changes over vendor, do we have a better sense of how it naturally changes based on height and weight and age and sex? Because it's there's so many levels of noise that does the open protocol help us reduce that noise so we can actually see what's more cleanly related to changes in that way, or is it not really as associated?
So I'm not exactly sure what is the question, but there is active investigations about the extracting information about covariates of age, sex, age. So there's René Labounek who worked on this with the span generic protocol, and then Sandrine Bédard and Yann Palochek also worked on extracting normative values, accounting for these covariates. And what we should be doing is also including scanner as a covariate. Yeah. In light of these results, absolutely.
All right. Any other questions? Merve, anything online?
No.
All right. Well, thank you, Julien.
Thank you.
Really appreciate it.